Oh, okay. Now we are live or not?
We are live.
Okay, so yes, so I start, and I want to start from a brief recollection of what I said last week. So the tetrahedron equation is a generalization of Young-Baxter and RLL equations, and in fact, what we see is that we have some plane in which we have something like Young-Baxter equation, and this is the plane of dashed lines here. And spaces which are involved are marked by numbers. And we have also spaces, additional spaces, which were not presented in the case of Young-Baxter. And those spaces are in normal direction to the plane, and additional operator R acts on this space, on these spaces. The equation has this form, and we push this R operator through the plane of dashed lines, and we can rewrite this in another form. So just multiply by R to the minus first on the right side, and get this form where now we think we consider dependence like action of these operators on a third space, which is of a different type, as a dependency of Lax operators on some probably non-commuting operators. So now this matrix is in contrary to the Young-Baxter equation, where matrix elements of R matrices are just numbers. Here, matrix elements of R operators, or here L operators, are some operators. So these are operator valued matrix. And this action by R matrix as by conjugation, we can think that this is like action of some internal automorphism of product of triple of such algebras. So A, VB, and VC, we think that this is like set of some generators of algebra of operators on space of this type. So here we have a conjugated set of operators, conjugated by R matrix which act in triple of such spaces. And as an associativity condition for this RLL equation, RLL tetrahedron equation, we get a functional tetrahedron equation, which involves now six, like to derive it, we have to take 6 Lax operators and multiply them and permute in 2 different ways, but with the same result. And statement that operators which conjugate this to get this are equal is statement of functional tetrahedron equation, which is equation for R matrices. Now, it doesn't involve these L operators. And the main, like this form, we can take classical limit of this equation. So now we go from algebra of operators on space F generated by V. As usual, we from operator algebra and classical limit, we go to some Poisson algebra. And like this Poisson algebra have Poisson bracket. So the main example which I discussed last week was this example, like I think constructed by Sergeyev and then explored further by Bozhanov and Sergeyev. And here Poisson algebra have two generators, x and y, and k square is 1 minus xy, and also 2 Casimirs, or just 2 numeric parameters additional in these Lax operators, and have this simple form. And this is matrix acting in tensor product of C2 and C2. So the auxiliary space in this problem is C2. And this is operator acting in tensor product of two copies of C2. If we write this, we can now write tetrahedron equation and solve it like a system of 8 by 8 system of equations, or 64 equations for those variables. And surprisingly, this system, so we can think that this kind of ansatz, and surprisingly, this is consistent ansatz. So we can solve this system and find a mapping of variables. And another surprise is that this transformation is canonical. So transformed variables x, y, k, lambda, and lambda mu remains unchanged, but x, y, and k, these variables satisfy same Poisson brackets as initial variables, which is kind of surprising and not obvious. And this is like consistency check for this theorem. And this what was known like in 2005, I think. Okay, any questions on this? Okay, if no questions, we go to perfect networks. And a perfect network is simple thing. This is some graph on, in our case, on plane or on disk, and on disk, better to think on disk. And this graph have two kind of variable vertices, black and white, and this is oriented graph, and black vertices are those which have exactly one ingoing edge, and white vertices are those which have exactly one outgoing edge. And this is like a defining property of this graph, I say. And this is the only constraint. And like external edges or half edges are divided in like can be ingoing and outgoing, and we call ingoing edges by sources and outgoing by sinks. And second half of data attached to perfect network is our weights, and we attach weight to each edge, or it's better to say to each half edge. And the weight is natural, so we say that if we have collection of edges, the weight of collection is the same as the product of weights. And if you have edge with the opposite orientation, we have weight to the minus first degree, and it's very natural. Sorry. And the last definition here is flow. So flow is just some subset of edges or half edges on this graph, which are not in from which we construct passes, and these passes are non-intersecting and oriented along the graph, and have their beginnings are sources, so they can't begin in the middle of graph, and they like ends are sinks of this planar network. And like we can define partition function of flows, and here A is some subset of sources, B is some subset of sinks, and partition function of flows from A to B is sum of all, like sum over all flows which go from this subset of sources to another subset of sinks over all weights of these flows. And here are example where all possible flows and they weights are written. So for example, this flow is 1 over gamma 3, and it have one source and one sink. And in this notation, this is flow from 2 to 1 prime. And important property of such partition function is like called Lindstrom-Gesell-Vinot lemma, and this is the lemma that it states that if we take some subset of sources and some subset of things and compute a partition function of flows, then it can be computed as a minor of matrix of flows in the sector with one flow. So Mij is a matrix whose matrix element in the column I and row J is sum over all flows which go from I to J of weights of these flows. And this is simple property, and we can very simply check it. For example, the simple check is to compute this as like this plus this times this minus product of these two. So this cancels, this product cancels one term, cancel one term here, and you get like this one term. And
may I ask a question?
Yes.
Does the first requirement mean that A and B are of the same size?
Yes.
Yeah, thanks.
Because this is path, and each path have one start and one finish.
In particular, all the starts and all the finishes are different.
Yes, because paths are non-intersecting. Yes. And the last object is a transfer matrix, and transfer matrix is just a matrix which contains all this, like in ordered way, contains all these partition functions. So how this is an operator which acts from C2 to the power of the number of sources to the C2 to the power of the number of things. And if we take one matrix element of this operator, we have to specify some subset of sources and some subset of things. And this is like spaces in which we take like spin up, and in all other spaces we take spin down, and this matrix element is equal to the partition function of flows from A to B. And here all these partition functions are collected into a matrix. So to make a connection with tetrahedron equation explicit, we need Poisson structure, and Poisson structure is defined on any, we define Poisson bracket to pair of weights of any passes, and take pass gamma 1 and gamma 2. The bracket is how is it called, quadratically constant. So the Poisson bracket of these two variables is proportional to their product, and this numerical factor is half integral and can be computed vertex wise, so vertex by vertex. And to compute it, we have to take all vertices where gamma 1 and gamma 2 intersect, and compute local intersection form of these passes. And it is computed in the following way. Let's think that we have this black vertex, and we have natural order on passes on these corners which go along this vertex. And we say that gamma 1, gamma 2, and gamma 3 are consecutive corners, and intersection form of two I and I plus 1 passes is equal to 1/2. And this form is skew linear and skew symmetric and linear. So this is enough to define intersection on any pair of passes through this vertex. And we also have sign +1 for black vertices and opposite sign for white vertices. So on this example, pick gamma 1 and gamma 2, and they have one intersection vertex, this one, and gamma 1 and gamma 2 are properly ordered in the clockwise direction, and because the vertex is white, we have to add additional minus sign. So Poisson bracket of gamma 1 and gamma 2 is minus 1/2 times the product of these variables. And the main statement of one of two main statements of previous part was that being properly conjugated by permutations, transfer matrix of this four-gonal block, which is written here, is equal to Baranev-Sergeev Lax operator, like depending on x, y, k, and lambda and nu. And this is a mapping of variables, and Poisson brackets are consistent. Questions here? Okay, so the second statement was about tetrahedron transformation, not Lax operator but products of three Lax operators. And to make it, we have to introduce first transformations of planar network. So there are two kinds of basic transformations. First one is two move, which is drawn here, and it transforms this graph to this graph. And in fact, we have also transformation of corresponding corner variables, and this transformation of corner variables can be made in such way that the like Poisson brackets of the first and second picture are consistent. And I skipped it here for just for simplicity of slides. And another transformation is a four move, and we can also define such transformation of corner variables, which which make transformation consistent, the consistent transformation of corner variables. And here is written not transformation of corner variables, but like products of corner variables. So x0 is product of four internal corner variables. For example, x1 is product of this corner variable times this corner variable, and so on. And if we take these products, we see the usual rule for those who know this is mutation in cluster algebra, or you can think that this is transformation of these path variables corresponding to blue passes. And here is a transformation of like Weaver, which encodes Poisson brackets of these variables. And like black arrow is for epsilon ij is equal to 1, and gray vertices are for epsilon ij is equal to 1/2. And the statement, like second main statement of previous talk, was that we can perform this tetrahedron transformation. So here we have product of Lax operator in one order. Here we have product of Lax operator in another order. And the statement is that this transformation can be made by a sequence of like probably eight transformations, which are two moves, which are, for example, first transformation is pair of two moves here and here, and four moves in some squares. Are some okay? So this was the main statement. And any questions? Okay, if no questions, I go to like things which I wanted to say today. And to go this. Sorry, do you see this panel on the top or not?
No.
Okay, but it doesn't want to hide. But if you don't see, this is okay. So now another piece of theory, and this piece about so-called factorization ansatz, and in fact, all this story with planar networks and their transfer matrices in the context of linear algebra, as far as I know, appeared from solution of the problem of total positivity in general linear group by Fomin and Zelevinsky. And they introduced networks like this network. So this is network. We say that such network is on 3 horizontal strands, and it corresponds to group GL3 or PGL3 to be more precise. And in fact, we can construct any network of this kind by picking like this kind of block or that kind of block, and compose them in various different ways. So we can draw here, or we could put something here or everywhere else. And it is convenient to encode these blocks using to put them into correspondence generators of double Weyl group. So S1 or S2 or S3 and so on are generators of Weyl group. And we put into correspondence to such block generator S1 and into correspondence to such block generator S1 bar. And here are transfer matrices corresponding to this these blocks. And we can take product of such generators. And if you have a block which interacts with first and second strand, we assume that it doesn't affect other strands if here are other strands, for example, third or fourth or fifth or so on. And the claim of Fomin and Zelevinsky was that the transfer matrix of the network with n horizontal lines, like here we had three horizontal lines, corresponding to reduced word W1 and W2, where W1 and W2 is some product of generators like S1, S2, S3, and so on. In the sector with one pass, in the same sense in which we said in the lemma by Lindström. And this transfer matrix belongs to double Breuer cell in GLN. And what is double Breuer cell, I don't want to define, but you can think that this is some subvariety in Poisson group, or Poisson-Lie group, in Lie group. And this subvariety is defined by the condition that certain set of minors vanish. So this network defines embedding of some torus defined by parameters into general linear group. Now to check that this map is well defined, that this is indeed mapping from Weyl group to to such expressions, to products of such matrices, we have to check that the relations in the group are satisfied or can be satisfied by basic transformations of planar networks. So here are two basic relations in double Weyl group. First relation is that two parts of this double Weyl group are commuting, So generators like S1 are commuting with generators like S1 bar. And in fact, this commutation can be performed by for move or spider move. And you can also check that S1 is commuting with S2 bar. And this can be checked by application of to move on a pair of white vertices on same line. And another, and probably the most important relation is Coxeter relation. And the Coxeter relation is a sequence of three transformations. So first you have to apply to move here and get this. Then you apply for move in this foregone, and you change colors of these two vertices and these two vertices. And then you apply to move here and get a product of generators, like of other generators. So S1, S2, S1 is equal to S2, S1, S2. If I say that this is a double Weyl group, I have also to check relations that S1 square is equal to 1. But there are some subtleties with this relation. I say about this relation as I square is equal to 1. And I don't want to touch this matter now because this is not that simple. And in fact, the relation which transfer matrices satisfy is Si square is equal to Si, and this is semi-group. But or half group, but this is enough to deal with reduced words, and this is why I written here reduced words. Okay, any questions on networks and double Weyl group?
Yes, Mykola, could you just repeat how the variables W are related with the network? I missed.
Variable where W is some word. This is word, for example, here W, in this example, W is equal to S1, S2, S1, and W bar is equal to like, no, identity, say identity. This is trivial word. And this word is just some rule how we write this network. So we have lines 1, 2. So we put, if we put black to white here, we put S1 here. Here we have lines 2 and 3 connected by this edge. So I can put S2 here because 2, 3. And here I have again S1. And if I have another colors on these vertices, I put S1 bar. So I put S1 here and S1 bar here.
Okay, thank you.
Mm-hmm. Okay. So, and our claim regarding these networks and double Weyl groups is that first obvious thing that there is a diagonal subgroup in double Weyl group generated by such products Si bar, and obviously such generators are also satisfying all the relations of Weyl group of type an-1. Or sorry, I should probably write here an, but this is not that important. And our statement, and it's also obvious that this block corresponding to Si bar, and it is drawn here, is exactly our block which we discussed before. Exactly this block, or say this block. And so the statement is that transfer matrix of this foregonal block which is S1, S1 bar, is tetrahedron Lux matrix. And this is the same object. And this is a generator, like generator of diagonal subgroup in this double wave group. And so any word which we can construct from any word belonging to diagonal subgroup is and corresponding Brouwer cell can be parameterized using only these tetrahedron Lux matrices. And tetrahedron relation itself, which is drawn here, is simple relation, Coxeter relation in this diagonal subgroup. So this is just statement that S1, S1 bar, S2, S2 bar, S3, S3 bar is equal to, oh, sorry. S1, S1 bar is equal to S2, S2 bar, S1, S1 bar, and S2, S2 bar. And this is like a trivial thing which follows from transformation which was presented on this slide. And like in more geometric terms, this is a statement that tetrahedron transformation relates to positive parameterizations for the largest Brouwer cell, which corresponds to the longest word in GeO3, largest Brouwer cell in GeO3. And functional tetrahedron equation, which I do not draw this here because it can take like a lot of place. But functional tetrahedron equation is a statement is that two ways to identify two different parameterizations for the largest Brouwer cell in GeO4 are equivalent. So as you probably remember, I said that functional tetrahedron equation is the statement that two ways to identify product of 6 Lux operators, two different ways are equivalent. And here we have product of 6 Lux operators, 1, 2, 3, 4, 5, 6, and here we also have 6, and like two rows are equivalent. Okay, question on this? Okay. So now I move toward integrable system corresponding, and I need like networks and cylinder for networks, and this is very simple generalization. So now I think that the network is contained not onto the strip, not in the strip from left to right, but on cylinder. And the only difference is that we can have edges which go along cylinder, like on another side of it, on the opposite side of cylinder. And in fact, we have to extend this double whale group, which we discussed in previous slides, by 3 additional generators. First generator, it is not drawn here, but this is a generator of this kind, but which connects opposite sides. So it is a generator of this kind, or better to make consistent notations. I should better draw it in this way. So what is drawn on by red is S0. Oh, not the bar, S0. And we also have a generator which have white dot here and black dot here. And this is S0 bar. And also additional generator is like loop rotation. So it just shifts all strands by one, but it doesn't contain any black or white dots. This is just shift. And important thing is that we have like branch cut here or just cut. And we additionally multiply or we additionally multiply all edge which cross this cut by additional weight, say lambda or mu, and this is spectral parameter, and this will play role of spectral parameter in the following. And this is like a mapping from matrices which do not depend on spectral parameter to matrices which do depend on spectral parameter, and a spectral parameter comes from edges which intersect cut. And so the corresponding combinatorial object which encodes these networks is so-called double extended affine wave group of A type. So we have all the same Coxeter relations written here, and we also have, and now generators are encoded by numbers from 0 to n-1, and we also have generator lambda, which acts by shifting of the indices of these generators. Okay, so I proceed, and now I want to compare two statements. And the first statement is the statement which was made, which I made on the previous talk, and this was statement of Bazhanov and Sergeyev, that if you take product, if you take n these Lax operators, their tetrahedron Lax operators, and multiply them along one space, two-dimensional space, auxiliary, auxiliary space, you get some another, and take trace over this space. So now this space is hidden. You get some operator which acts in the product of another spaces, so 1, 2, and so on to n. So this is 2 to the this is space of dimension 2 to the power of n, and this as we work in classical limit, this is a matrix depending on some Poisson variables. And their statement was that this matrix decomposes into blocks, and sizes of these blocks are binomial coefficients k to the n, and like these blocks of this block matrix are Lax operators with auxiliary space case fundamental representation of Cn, of GLN, and these Lax operators satisfy classical R-level equations which with the trigonometric R matrix. So, for example, in sector with one path, which is the main sector, this is just n-dimensional, like n by n matrix, and these n by n matrices satisfy Young-Baxter, classical Young-Baxter equation, not classical, but classical R-level equation, which with trigonometric R matrix. And spectral parameter comes from like dependence, in fact, from this lambda and mu, which was T numbers here, lambda and mu. And
Is capital N and little n the same time?
sorry?
In your formula of
Yes,
for the
this is
bracket.
mistake. This is small n. Yes, not capital. But sorry, this is mistake. Yes. So this is the Lux operator. And another statement which was made in completely different reasons, not but in the same reasons, but like unrelated, completely unrelated statement, was made by Gechtman, Shapiro, and Weinstein. And this was a statement about Poisson structure on passes. And they proved that if you take transfer matrix of any perfect network of passes on any perfect network on cylinder in the sector with one pass with equal number of sources and drains. Network have to contain equal number of sources and drains. This transfer matrix satisfies classical parallel equation also with spectral parameter. And this spectral parameter comes in the way which I said. So you have some branch cut on this cylinder, or just cut on this cylinder, and you multiply or passes which cross this cut by spectral parameter. And such objects, such transfer matrices in sector with one pass satisfy also classical parallel equation, where Poisson structure is those structure which are defined for pass variables on this network. But this is the same matrix. And now it's very natural.
So this lambda and mu are no longer related with gammas?
So you ask if lambda can be expressed with gammas, yes?
In this statement, like you say, in contrast to previous ones, these lambda and mu are not related at all to gammas. Are they?
I have to say that they are not, yes. This is some additional parameters. And as I said, the parameter comes from like those passes which intersect this branch cut. I think so. Any other questions? Okay, so I can proceed. And like both considerations results the same consequence that you can take characteristic polynomial of this characteristic polynomial or of this operator or of this operator, and now you have spectral parameters lambda and mu, and coefficients of this characteristic polynomial, which are Hamiltonian or commuting Hamiltonian of integrable system. And this follows from classical parallel equation.
Sorry, I do not understand. So first of all, you don't need any normalization here. So yes. This Poisson bracket is this Poisson bracket on paths, and you say that this is automatic. This is satisfied automatic.
Yes.
But still, you cannot say anything about integrable system before counting, right? How many variables do you have, and how many commutational conditions do you have?
Yes, and in fact, Zhanov and Sergeyev, they know what integrable system they got. They got classical XXZ chain, and they like integrability followed from the knowledge that the system is integrable. And like in Gechtman, Shapiro, and Weinstein, they in original paper about networks, they didn't make a statement about integrability. and they made the statement in the in the following paper, but for very particular network, for a network corresponding to Toda chain, and they didn't made, as far as I understand, they didn't made integrability statement. They said just this, and
does it mean that here it's impossible to count, unlike these cluster variables where this is a simple counting argument, how many phase variables do you have, how many Casimir functions, and how many, and the rest is integrals of motion, yeah? And here there is no simple counting.
yeah, as far as I understand, there is no counting, yes. And in fact, so the general theorem about integrability, it comes from counting of passes already on torus. So in fact, what we do here, we take determinant can be decomposed using traces of or minors of this matrix. And in fact, counting of these minors and this summation corresponds to computation of a partition function of passes on torus. So now we say about all passes on torus, and if we know partition, if we know transfer matrix of passes on strip or on cylinder, we can glue sides of a cylinder or pairs of sides of disk, and this gluing is is a function which maps one side to another and one side to another, and which puts things to sources and sources to things. And the only thing apart from taking traces is insertion of spectral parameter. So we for each glued side we count path which intersects this side with orientation, and if it crosses this cut in one direction, we take first degree of spectral parameter, and if it crosses cut in another direction, we take minus first degree, and similarly with another cut. And by taking trace of all necessary over all necessary spaces, we get some number which is partition function of passes on torus, of non-intersecting passes on torus. And in fact, general theorem was proved by Goncharov and Kenyon, and in their theorem, they again say that we have spectral curve, which is the composition of this partition function over degrees of lambda and mu. And coefficients are some expressions depending on Poisson variables, and these Hamiltonians are commuting. And they also proved that this proved counting lemma, and they compared number of variables.
I'm confused now. What is the bracket in Goncharov and Kenyon?
The same as here.
So it's defined on paths.
Yes.
But no, not with the help of this dual surface, just on path like you defined.
Yes, this is the definition. Yes.
So it's kind of different statement from the statement with another bracket.
Why? But these two brackets coincide. This is a definition from their appendix.
To my knowledge, with that bracket, which I seemed to understand, their lambda and mu variables are not Casimir functions. and they compute Poisson brackets of, or they have non-trivial Poisson brackets with dynamical variables.
From this point of view, you can think that lambda and mu, which I introduced, are some additional parameters. Like
So in your cases, as you told me, they're obvious Casimir functions because they're extra parameters.
Yes.
And what I heard of from Kenyon, that his lambda and mu, they have non-trivial brackets with dynamical variables.
Okay, I cannot like say for Kenyon, but the theorem which they proved in their paper is this kind of this theorem. Probably they like extracted from Hamiltonian some additional contributions in these degrees, which correspond to some passes which like have class in homology 0, 1 and 1, 0.
Well, at least naively, their lambda and mu are different from your definition of lambda and mu. Because indeed, they are sort of associated to homology classes on torus, and
Yes.
In that sense, they are not even defined uniquely.
In this theorem, if you look into their formulation of this theorem, they don't have lambda and mu at all. They have, yeah, you can just look and
let's then postpone this. But
the
point is, yeah. So
yes, but they don't have spectral parameters. They like classify all contributions to partition function by the Widen class, by the class in torus homology, and they like don't extract spectral parameters. They just say that we sum over all contribution to like all like collections of passes which contribute into class AB in torus homology.
Then you at least reformulate the theorem in some different language.
Yeah, trivial reformulation. Yes.
That's then it's very confusing. Okay.
Sorry.
But I'm afraid that if you try to introduce spectral parameters as some products of weights, they will actually be non-commuting. But in this case, these Hamiltonians will also be non-commuting. So probably it's a bad way to do.
I don't know what is it good way or bad, but I just say that like it's written in Colli's transparency is unclear what kind of statement of Goncharov and Kenyon he makes.
But in fact, I made this because I used two different languages. One language is of Goncharov and Kenyon, and another of Gehman, Shapiro, and Bernstein. And like not to confuse everybody, I tried to like bring these two languages together. So this is sorry for confusing. Okay, so now we have integrable system, and just to recollect all what was said for last 15 minutes, if you take some perfect network on torus and compute partition function of all passes on this torus, and consider only those passes which contribute into class like AB in torus homology, you get Hamiltonians of integrable system, commuting Hamiltonians. And now, example, so in fact, all what remained is two examples. And the first example is, in fact, the example from original paper of Bazhanov and Sergeyev, and it is very simple. You just take take a look onto this first column. This column is product of Lax operators along one space, green space, and each rhombus here is such four-gonal block or block corresponding to Lax operator. And here we take product and take trace, and on the one side it was proved by Bazhanov and Sergeyev that their Poisson bracket is like trigonometric Poisson bracket, and from another side it was proved by Yechman, Shapiro, and Weinstein that, but now in the language of passes, that the Poisson bracket of two such blocks is trigonometric R matrix, like trigonometric parallel equation, like transfer matrices of these blocks satisfy trigonometric parallel equation. And now, for example, we can take product of two such blocks, or so on, so on, so on, and what we get is like monodromy operator for this is the usual formula that if you take product of Lax operators, and here we have product of two Lax operators, and each Lax operator satisfy trigonometric parallel equation. And their product is also satisfying trigonometric parallel equation. And now we get monodromy operator form for XXZ classical XXZ spin chain on two sides. Two sides because we have a product of two Lax operators here. And by stacking more such blocks, you can get some larger integrable systems, and 3 sides and 4 sides and so on. And the nice thing which is clear in this formulation is spectral duality. Spectral duality says that in fact spectral curve and they share same phase space. XXZ spin chain GL3 classical XXZ spin chain on two sides share spectral curve and phase space with GL2 classical XXZ spin chain on 3 sides. And in this formulation, it becomes clear because we could consider this as monodromy operator from left to the right and keep these spaces free and taking traces over this. And then finally, when we multiply these two, take traces here or determinant to get spectral curve. And we can act in the in another way. We can keep these spaces free and take traces here. And so we have a two-dimensional auxiliary space in the sector with one path here. And we get Lax, each this block gives us Lax operator of GL2 chain. And then we can multiply 3 such blocks and get GL2 on 3 sides by taking multiplication of 3 such operators. So, and this is a statement of spectral duality that determinant of lambda minus monodromy operator of GLs 2 on 3 sides depending on mu is equal up to some factor which is not important but which depends on lambda and mu to spectral curve of GL3 spin chain on 2 sides depending on spectral parameter lambda. And in this formulation, using these blocks, it's like obvious statement. And now we can generalize this, like using knowledge that we can like take any products of such blocks in any order and any directions, and still get something which satisfies a classical Arrow equation by theorem of Yechman, Shapiro, and Bernstein. We can generalize this. So, for example, we can take this kind of network. So I take some different product of flux operators, and we can take trace, for example, in this direction. And transfer matrix of passes here have auxiliary space four-dimensional, and four-dimensional, and theorem by Yechman, Shapiro, and Bernstein still gives us that this satisfies a Arrow equation. But we can still keep us only using these orthogonal blocks and using like no more building blocks apart of this. And in fact, a theorem like lemmas proved by Goncharov and Kenyan allows us to reconstruct spectral curve simply, not spectral curve, but Newton polygon. We can predict Newton polygon of integrable system without, in fact, taking multiplications of all these operators. And the recipe is the following: if you take product of these operators, you have to just think that you have crossing of some passes here in each rhombus, and then you consider all passes which go like this, like thick passes, which are drawn by green and red here, and you each pass have some class in homologies of torus, and here the class in homologies, for example, of this red pass is 1, 0, and this is 1, 0, and this is 1, 0. And of this green is 0, 1, and of this is also 0, 1. And now you double this pass, so you add to this like the same with the opposite class in homologies, minus 1, 0, minus 1, 0, and here you take 0, minus 1, and here also 0, minus 1. And now you have a set of some vectors in Z square. And sum of all these vectors is 0. And if you have some set of vectors in Z2 and their sum is 0, you can always construct unique up to translation Newton polygon from these vectors. Newton polygon means that some convex polygon with integral vertices. And here it's easy to see that the polygon which can be made from all these vectors is this polygon which is drawn. And like these 1, 0 vectors are bottom side of this polygon, and this 0, 1 are right side, minus 1, 0 is top side, and 0, minus 1 is left side. And this is how we obtain from this drawing, we obtain Newton polygon. And the final thing which I want to say is to show how this can be made for this example, and this with the same simplicity can be made. I just look for some. I take some paths and look what is class in homologies of this path. So I go along here, then here, then here, and here, and here. It's very long, and it's easy to see that its class is 3, 2 in torus homology, and I have to like double it and add also class with opposite class, path with opposite class in homologies, -3, -2. Now for the red, it's simple to see that its class is -1, 1, and I double it by adding path 1, -1 with the opposite class. And for blue path, we have 0, 1, and opposite is 1, -0, -1. And again, sum of all these vectors is 0 in like 0 as a vector. And we can construct a unique Newton polygon from them. And this Newton polygon is drawn here. And statement is that if you now compute spectral curve for this system, like by computing trace of spectral curve of monodromy operator, this is sum of Hamiltonians times spectral parameters, and here A and B belong to some polygon, integral polygon, and this polygon is exactly this Newton polygon which is drawn here. So, and internal vertices of this polygon correspond to Hamiltonians of this system, and boundary vertices are corresponding to Casimirs of the bracket. And so they have Poisson bracket 0, which among themselves, and in fact with any phase variable of this integrable system. Phase corresponding to closed phase on perfect network. And probably it's a good place to finish. Okay, questions?
Okay, may I ask two
Yes.
questions?
Mm-hmm.
The first question is about that those commuting Hamiltonians and all integrability stuff. Can you just solve all these equations in the finite zone style, and then everything will be as clear as possible? Because as I know, if you have discrete time systems based on such things like tetrahedron relation, then everything can be solved exactly in terms of a spectral curve and divisors. You see those divisors go according to some evolution described in a very clear and explicit way. So this is the first question.
But this is nothing new here. I mean, this is the usual finite zone integrability, like by Krichyver, where you have spectral curve and like Lax operator, and by Lax operator you can construct divisor, and this divisor you plug it into theta function and get solution.
So you can do this.
Yes, this is not my knowledge. This is very classical thing.
Okay, very good.
But Koля, if so I did I understand correctly that this question was about discrete flows in the system or not? Or was it about continuous flows?
Sorry.
The question was about continuous dynamic or discrete?
Yes. The question was about continuous dynamics.
Yeah.
And, about discrete dynamics, I know already. Okay, but the second question is, you have written here those beautiful networks, and you see they remind me the dimer model. Dimer, you see the dimer model in my own work, but I could not understand on the fly. Can your networks be somehow represented in terms of dimer model or not?
Yeah, you're completely right. And in fact, this is like a work of Goncharov and Kenyan was made in the language of dimers. In fact, all they made sorry, I have to go. All they made by what Goncharov and Kenyan made, they made in terms of dimers. And in fact, as far as I understand it, I read your paper on dimers. This is the same dimers, yes.
Okay, thank you. Yes,
You're right.
Коля, as far as I remember, maybe I'm incorrect, but in Kenyan's and others' works, there was integrable systems based on dimers model. And there was nothing, as far as I remember, related to tetrahedron equation.
Yes,
that's an interesting question. And
so what the relation or interrelation between these dimer type models and tetrahedron give new way of thinking or new representation? What new was brought by the observation that tetrahedron equations and planar networks are interrelated?
On my opinion, first is the observation that we can construct integrable system with any spectral curve. So if you find now some other solution to tetrahedron equation, you can try to multiply these Lax operators not only as a regular grid, but you can try to multiply them using some more complicated pattern, like this pattern. And you can still expect that the resulting partition function is something meaningful and something related to a spectral curve with such Newton polygon. And this is what was not known in works.
Does the tetrahedron equation helps with this question? Or it's just the equation about constructing some discrete difference operator on some grid, not with tetrahedron equations.
Yes, but it have nothing to do with tetrahedron, but it have to do with clusters. But the object is the same. So we can use property known in one side in another side and try to make it reasonable, or like to apply it in other cases which are not related to cluster algebras.
I'm lost. Are you saying that you can construct new solutions to the tetrahedron equation? No. But what is the new? It is known that there is an integrable system corresponding to any Newton polygon.
But this what was known in cluster algebras, not in tetrahedron science. And now we know that using tetrahedron we can construct integrable system with any Newton polygon.
Why? Well, it's the theorem of Goncharov and Kenyan, or or Shapiro-Weinstein, whatever, that for any convex Newton polygon, you construct an integrable system in some way.
Yes,
so
you're right.
What is new in this?
This is nothing new in general for science. The new is correspondence.
I would say that Kola invented a way to represent some concrete algorithmically built a network which describes a concrete Newton polygon, because Genshiro and Kinin tell us something like, let us draw those lines on a plane, then move it such that there are only triple intersections and so on, and there is no explicit way how to do this.
You just say about some concrete Lax representation for that integrable system, right?
Yes.
For constructing Lax representation.
Yes.
Yeah. Okay. Yeah. That's clear. Yes.
Okay, Nikita, you wanted to say something?
Yes. I wanted to. I mean, I was. Unfortunately, I missed the previous lecture, but I thought when the announcement came that the discussion would be about the relation of the scattering in 3 dimensions, which the tetrahedron equation represents, and maybe the like the growth models in 3 dimensions, which can be described by dimers, which are described by cluster integrable systems. So that dimers in 2 dimensions are projections of 3-dimensional structures.
Yes.
Maybe the 3-dimensional structures somehow are related to the scattering of which the tetrahedron equations describe.
But I have to say that the 3-dimensional symmetry is broken here, because we have Lax operator with 2 2 auxiliary spaces of one kind and third dimension of another kind. And what I skipped here is quantum version. So I worked classically, and when I say, sorry, I have to draw. When I say about quantum, counterpart of this story, it have this structure. And here you have this R matrix.
Mm-hmm.
And probably using this R matrix, we can say something new and interesting about 3-dimensional box counting, which you ask about. But this is like the story for further investigations.
Okay.
And but in fact, all these passes which I was talking about during the talk are projection of these boxes. Yes, and this is very interesting story. And like the story becomes very interesting when you consider not networks on torus, but networks on plane. So when you iterate these blocks infinite number of times in the left, in the right, in the top, and in the bottom, and like shift spectral parameter or deautonomizируйте this system, like de-autonomize this system, you get something very much related to topological strings partition functions.
Colin, but this is usual relation of integrable and isospectral and isomonodromy equations. Again, what is missing for me is the real role of tetrahedron. You see, whatever you say at the end, it's about integrable system, which we, to some extent, understand. What's the role of tetrahedron equation in the theory of integrable system? It's still some relation, but it's, in my view, it's up until now, it's very poor understood.
Oh, but Igor, but here, as I understand, what Kola says is the following: that tetrahedron equation is some natural relation which appears for some blocks of this Lax operator, how he constructs it. And actually, it's equivalent to some Coxeter properties of these words, which are in the heart, at least with our construction with Fock, and which were not noticed before. So it's kind of a relation of different. So as I understand, indeed, as Pasha said, that this is some concrete algorithm for constructing this Lax operator. So this Lux operator is not unique. So, for example, our theorem with Fox says that for each Newton polygon, you can construct something on the Poisson submanifold in this coextended Lie group, but in an ambiguous way. There are many such possible constructions. And so and they are related with this different representation for these words in double Weyl group. What Kolle says is that some natural relation for in a Poisson submanifold of PGL4 gives you tetrahedron equation. And that, well, I don't know much about tetrahedron equations, but I never heard about this before.
No.
We're
not discussing the appearance of tetrahedron equation is new, but it's not. It's just a remark. That's
an observation.
An observation, yeah, maybe not yet understood.
No, that's what I'm saying.
So, for example, what Nikita says is some physical way to understand it. Yeah, I don't know, of course.
I'm saying it's missing, but
no, you have some
would be desirable.
Words attached to it, but okay, yeah, it's missing yet. But it's interesting observation because
no.
Especially for those who don't know what is tetrahedron equation.
Now, you see, it would be interesting to. Young-Baxter equation gives you integrable statistical models. So, what's the use of tetrahedron?
Igor Misich, I have some remark. I'm not sure that is coherent in this subject, but in some other subject, it is more related with the dimension growth. So it represents the an integrable system with a family of integrals of bigger dimension. So if you consider the Young-Baxter equation represent integrability property for the one-dimensional chains, and if you consider the two-dimensional lattice, you have the family of commuting integrals of big dimension. I suppose this is a significant meaning of the tetrahedron equation. I'm not sure that it is applicable in this situation of Mykola talk.
Okay, it seems that sooner or later in future we'll have another talk.
Actually, what bothers me is that this Young-Baxter relation, you can simply reformulate in terms of a Poisson bracket. It's just a Jacobi relation for Poisson bracket, for this classical Poisson bracket with this classical R matrix. And Kolya, am I right that there is no such simple meaning of tetrahedron equation?
Classical, but in quantum, as I said, on a quantum level, it is associated, like functional tetrahedron equation is associativity condition, and this is like
some kind of quantization already.
Yes, associativity condition is quantization of Jacobi relation.
Yeah, but that's Young-Baxter.
Yes.
No.
And not tetrahedron. And tetrahedron is something more thin, yeah, more detailed.
And here, this is like associativity condition for product of 6 Lux operators. And this is what.
Sorry. Also, tetrahedron equation and similar things are associated with inhomogeneous models like dimer model or inhomogeneous 6-vertex model. You see, Young-Baxter more or less deals with statistical physical models 2-dimensional and more or less homogeneous or with simple inhomogeneities. But tetrahedron equation or similar things that give you an evolution of Boltzmann weights of a inhomogeneous statistical physical model, 2-dimensional. And this evolution conserves the state sum, the statistical sum, just such a simple observation.
Mm-hmm. And
where do the inhomogeneities take values in this case? So for
sorry?
inhomogeneity is like a complex number, or maybe it lives on an elliptic curve. But for tetrahedron, where do inhomogeneities live?
In homogeneity, imagine just, for instance, a regular lattice, be it a square lattice, two-dimensional, or Kagame lattice, and you somehow place on it either a dimer model or a six-vertex model, but with Boltzmann weights depending on the site, depending on different in different vertices. So and then you can define a sort of discrete time evolution. At least that's what I know personally. You can define a discrete time evolution which changes these Boltzmann weights in such a way that the state sum remains an integral of motion. Well, actually, it depends. There is not one state sum. There is a whole bunch of them, and they form essentially they form the Jacobi torus, on which the already mentioned divisors travel linearly in that discrete time. Have I answered your question?
Sort of, yes. Yes.
Any comments or additional remarks?
I have a question to Kolya. Are you still want to listen to Boris Lvovich?
But probably I missed already. So
Okay, so thank you, Kolya.
thank you for asking questions.
Thank you.
Пока.
Bye-bye.